In 2006, Pluto has never really let go of the public imagination, and recent discoveries suggest it may be far more complex than we ever dreamed. Once seen as a cold, dead rock lurking in the Kuiper belt beyond Neptune, Pluto has emerged as a surprisingly dynamic and geologically intriguing body that is changing how scientists think about planetary formation, habitability, and even the origins of life itself. Much of what we know today comes thanks to NASA's New Horizons mission, which flew past Pluto in 2015, delivering spectacular images that revealed a world of icy plains, towering mountains, and a vast heart-shaped basin named Sputnik Planitia. These images overturned the long-held notion of Pluto as a simple frozen ball. Instead, they showed a landscape scarred with fractures, hints of ice volcanoes, and surprisingly few impact craters in some regions, signs that Pluto may have experienced recent or even ongoing geological activity. This possibility has prompted scientists to reconsider whether Pluto might harbor a subsurface ocean beneath its icy crust. Such an ocean, kept warm by residual heat from radioactive decay or tidal interactions with its large moon Charon, could remain liquid despite Pluto's frigid surface temperatures, which average around -375 degrees Fahrenheit -225 degrees Celsius. The idea of liquid water beneath Pluto's frozen shell is not merely speculative, it's supported by multiple lines of evidence. For example, the alignment of Sputnik Planitia almost directly opposite Charon suggests that its formation may have shifted Pluto's orientation, a process known as true polar wander. This realignment would be far more plausible if a subsurface ocean existed to allow the crust to slide over liquid layer. Only a small percentage of models reproduce such an alignment without a liquid ocean, making the hypothesis compelling. Meanwhile, the chaotic terrain on Pluto's far side shows cracked and distorted features reminiscent of similar zones on other planetary bodies like Mars, Mercury, and Jupiter's moon Europa, where impacts are believed to have sent seismic waves converging on the opposite hemisphere. Computer simulations by researchers such as Purdue University's Alan Denton suggest that a subsurface ocean would be necessary for such seismic waves to produce the observed chaos on Pluto's surface. These clues, taken together, point strongly toward the existence of liquid water, a fundamental ingredient for life as we know it. The potential for habitability is further bolstered by the discovery of cryovolcanism on Pluto. Unlike the lava-spewing volcanoes on Earth, Pluto's ice volcanoes would erupt with mixtures of water, ammonia, and methane, materials that could transport nutrients and energy from the interior to the surface. Such activity indicates that Pluto's interior remains warm enough to sustain reservoirs of liquid water. Indeed, two large ice volcanoes identified in New Horizons imagery, informally named Wright Mons and Pickard Mons, show few impact craters, suggesting relatively recent geological activity. Cryovolcanism could help cycle organic compounds and heat, potentially creating niches where microbial life might survive. Pluto's atmosphere, though thin and ephemeral, adds another layer of complexity. Primarily composed of nitrogen with traces of methane and carbon monoxide, the atmosphere undergoes dramatic seasonal changes as Pluto travels along its highly elliptical 248-year orbit. When closer to the Sun, its surface ices sublimate, thickening the atmosphere. Farther away, the gases freeze out, collapsing it. These cycles create dynamic weather patterns and temperature variations that can drive further geological changes. Observations of hazes extending over 200 kilometers above Pluto's surface reveal layers of hydrocarbon particles formed when sunlight breaks down methane in the atmosphere, giving Pluto a surprisingly blue-tinged sky in images and altering its thermal balance. This haze affects the temperature structure of the atmosphere, making it even colder than expected while also contributing to Pluto's reddish surface coloration through the deposition of complex organic compounds called tholins. These tholins form when ultraviolet radiation interacts with methane, creating complex hydrocarbons that may be precursors to the building blocks of life. The discovery of tholins on Pluto is especially intriguing because similar organic molecules have been found on other icy worlds that are considered promising candidates for life, such as Saturn's moon Enceladus and Jupiter's moon Europa. On Earth, complex organics are fundamental to the chemistry of life. If similar processes are occurring on Pluto, it raises profound questions about whether life, at least in microbial form, could exist in such an extreme environment. Extremophiles on Earth have taught us to expand our definition of habitability dramatically. Organisms thrive in boiling hydrothermal vents, acidic pools, subglacial lakes, and deep oceanic trenches, proving that life can adapt to conditions once thought utterly inhospitable. If liquid water exists beneath Pluto's icy crust, warmed by internal heat and enriched by organic molecules cycling between interior and surface via cryovolcanism, it could provide a stable environment for such hardy organisms to develop and persist. The relationship between Pluto and its largest moon, Charon, further complicates this picture in fascinating ways. Charon is unusually large relative to Pluto, with a diameter over half that of its parent body. This results in a binary-like system in which both bodies orbit a common center of mass located outside Pluto itself. They are also tidally locked, always showing the same face to each other. These gravitational interactions could help maintain internal heating in Pluto by flexing its interior, potentially sustaining a subsurface ocean over billions of years. Charon itself shows evidence of a complex geological history with massive canyons, smooth plains, and possibly even ancient cryovolcanic flows of its own. Studying this dynamic duo provides insight into the evolution of icy bodies throughout the Kuiper Belt. Beyond the intriguing possibility of subsurface oceans and organic chemistry, Pluto offers a crucial window into the history of our solar system. As one of the largest known Kuiper Belt objects, Pluto is a preserved relic of the early solar nebula from which the planets formed. The Kuiper Belt is a reservoir of ancient icy bodies that were left behind when the giant planets migrated to their current positions. By studying Pluto, scientists can learn about the composition and dynamics of these primordial leftovers, helping to answer questions about how our solar system evolved and how similar processes might unfold in exoplanetary systems. The New Horizons mission revolutionized our view of Pluto, but it also highlighted how much we still don't know. Low-resolution images hint at further secrets lurking on Pluto's far side, beyond the reach of the spacecraft's brief flyby. Future missions could orbit Pluto, mapping its entire surface in detail, analyzing its thin atmosphere over time, and even probing for evidence of that elusive ocean beneath the crust. Such missions would not only reveal Pluto's internal structure, but also help refine our understanding of the conditions necessary for life to arise and persist in extreme environments. Pluto's reclassification as a dwarf planet in 2006, driven by the need for clearer definitions as more similar objects were discovered in the Kuiper Belt, initially seemed like a demotion that might consign it to obscurity. Yet, in many ways, this change has had the opposite effect. Freed from the expectation of behaving like a classical planet, Pluto has become emblematic of the rich diversity of worlds in our solar system, reminding us that planetary science is about understanding all worlds, large or small, and their roles in the grand tapestry of cosmic evolution. Its geological complexity, potential subsurface ocean, organic molecules, dynamic atmosphere, and interactions with Charon make it a natural laboratory for testing theories about planetary formation, internal heating, atmospheric processes, and the potential for life in extreme conditions. Even its vivid surface features, icy mountains as tall as the Rockies, vast plains of frozen nitrogen, and reddish organic stained regions sculpted by alien winds and seasonal cycles, tell a story of a world that is anything but static or dead. Instead, Pluto emerges as an active, evolving body that challenges our assumptions and demands continued exploration. As scientists and space agencies consider future missions to the outer solar system, Pluto stands out not only for its scientific value but also for its ability to capture the human imagination. Its story is one of discovery and reinvention, of moving from the ninth planet to a dwarf planet, to an icon of the uncharted frontier that lies beyond the known. It is a story that reminds us that the cosmos is full of surprises, that our definitions must evolve with our understanding, and that every distant point of light in the sky may hold secrets waiting to reshape our view of the universe. As we continue to study Pluto, both from afar and hopefully someday up close again, we will not only learn more about this fascinating world but also about our own planet's place in a dynamic, evolving, and richly populated solar system. Pluto's evolving story also underscores the value of exploration itself. Every mission that journeys into the solar system's outer reaches brings with it the potential to upend what we thought we knew. Before New Horizons, Pluto was nothing but a blurry smudge, even in our best telescopes, a symbol of mystery at the solar system's frontier. Its transformation into a richly detailed, surprisingly active world was a dramatic testament to the power of direct observation over assumption. This lesson is critical not just for Pluto but for the many other icy bodies that populate the Kuiper Belt and beyond. These distant worlds are like frozen time capsules, preserving the conditions of the early solar system, offering clues about how the giant planets migrated, how volatile compounds were delivered to the inner planets, and how small bodies can remain geologically active even billions of years after formation. By studying them, we gain a better understanding of Earth's own origins, of the processes that brought water and organics here, and of how habitable environments might emerge elsewhere. Moreover, the technological achievements of missions like New Horizons demonstrate what humanity is capable of when we choose to explore. The spacecraft had to travel over 3 billion miles in a precise trajectory, using gravity assists and intricate planning to reach Pluto on time for its brief high-speed flyby. It carried the hopes of scientists who had waited decades for a closer look. And in just a few hours, it delivered a torrent of data that will be analyzed for decades more. This model of patient, ambitious science is a powerful counter to the short attention spans and quick return expectations of modern life. It reminds us that some of the most profound knowledge requires decades of planning, years of travel, and humility to accept that answers will often lead to new questions rather than final certainty. In this spirit, the idea of sending an orbiter to Pluto has gathered support. Unlike New Horizons' one-time glimpse, an orbiter could circle Pluto for months or years, mapping its entire surface in high resolution, monitoring seasonal changes in its atmosphere, measuring heat flow from its interior, and potentially even using radar to probe beneath its crust for signs of a subsurface ocean. Such a mission would be a natural next step in the tradition of exploration that turned Mars from a distant point of light into a world with rovers trundling across its surface, or that transformed our understanding of Jupiter's moons from icy points of light to potential ocean worlds. The challenges would be immense: a round-trip communication time of up to 10 hours, extreme cold, long-duration reliability demands. But the rewards could redefine planetary science yet again. Pluto also serves as a reminder of the emotional side of exploration. Its reclassification in 2006 provoked fierce public debate and disappointment, but also a sense of curiosity and determination. Far from being forgotten, Pluto became a symbol of how science evolves with new data. The very act of asking, "What is a planet?" forced astronomers to think more carefully about categories and definitions, leading to new insights about dwarf planets, exoplanets, and the diversity of solar system bodies. In many ways, Pluto's demotion liberated scientists to appreciate it, and others like it, for what they are rather than what we expected them to be. This humility in the face of nature's complexity is at the core of good science. Ultimately, Pluto's significance transcends its physical characteristics. It represents the human drive to understand, to reach out into the unknown despite enormous distances and long timescales. It stands as a monument to our curiosity, our technological ingenuity, and our willingness to be surprised. Even now, decades after its discovery, Pluto continues to challenge assumptions about where and how planets form, about what conditions might support life, and about the sheer variety of worlds that share our Sun. It hints at the thousands of icy objects yet to be studied in the Kuiper Belt, at possible ninth planets lurking even farther away, and at the countless exoplanetary systems we are only beginning to glimpse. In its cold, distant orbit, Pluto shines as a beacon of the scientific spirit, urging us to keep exploring, keep asking questions, and keep seeking our place in the vast, mysterious universe.